In this problem, we're going to compute the value of an interest earning account where R of t is the revenue stream that's flowing into the account. Now, in the past, we had done calculations involving continuously compounded interest, where we said that the total amount in the account over time would be PE to the RT. However, this is an example where there's just one payment made at the beginning of the principal P, and it would earn continuously compounded interest throughout time. So in that case, what we would see is that we start up here at some value P, and it grows to some new value. But that's a one-time payment. This is different now because in this problem involving future value, there will actually be payments made to the account all the time. It's not just discrete payments where they're made yearly or monthly or daily. The income is flowing into the account continuously. So it's a little different from the way that we had calculated things in the past. The formula involves an integration, but this time we're not just integrating the total value, like we're not just integrating how much money is being paid into the account, we also want that money to be earning interest. So if we look at this very most basic type, where we have a constant 20,000 being earned over 20 years. And in the past, we found the total value by integrating from 0 to n of that 20,000 dt. Okay, but we want this money to earn interest. And so the future value has a little bit different formula. It'll be an integral from 0 to n of R of t, but not just R of t, but R of t times this new term, e to the r n minus t. This is the interest earning part of the formula. And we need to do n minus t because we want to figure out how long that particular amount of money is going to stay in the account and earn interest. And the subtraction gives us the time that that money will stay in the account. So let's try it for this example. We'll go from 0 to 20. Our function is 20,000. Now we need an e, and we want to raise it to the r times n minus t. So r is going to be our interest rate, our APR. And for n, we actually want to plug in the same number that we had put as our upper bound. So let's do 20 and then leave our t as a variable because we're integrating with respect to time t. That's the integral we want to do. You can do it with a TI-84 plus CE calculator, and you can also do it using an online web app if you want to evaluate this quickly. So I'm going to go to the online web app here. I'll use symbolab.com to answer the question. We just have to type the integral exactly as it had been written on our page. And the online calculator can give us an approximation of this answer here. All right, it gives us 687,312.73. And with finance math, we typically want to round to the nearest cent. And that's our answer. In a previous video, I had integrated the revenue stream to find the total value of this same account. The total value came out to $400,000. So even though we paid in $400,000, because the interest was earning on the account all the time, our future value will be $687,000. So it's actually going to be worth much more than $400,000. If we subtract future value minus total value, we can actually get the interest earned. So I'll just do that real quick here. Let's see, we're going to earn $287,312.73. We're going to earn about $287,000 in interest for this account, which is substantial. Now let's revisit a topic that we had looked at in the past, and that was discretely compounded interest for an annuity. This is similar to an annuity in that payments are being made all the time. The only difference between the formula above and the formula below is the one that we're about to do here in part B is actually for discrete situations like monthly payments, daily payments, etc. Whereas the integration above is for continuous payment. So let's go ahead and see how close the discrete formula would come to the continuous formula. I'll plug in my payment amount for daily payments. So since we're paying $20,000 per year, how much would that be if we were to spread it out over 360 days? We're using the banker's rule here, which is an approximation of the number of days in the year. Pretending that it's 360. So let's divide the 20,000 by 360. And that tells me I'm going to make about $55 in payment. And I'm going to keep a lot of decimals in the calculation. That's usually standard for these problems. Okay, then we're going to multiply by 1 plus 0.05 over 360. Raise that to this 360 times 20. Subtract 1. And then divide by 0.05 over 360. All right, let's see what we get. Okay, with the annuity formula, I get $687,237.23. So awfully close. It's awfully close to the value we had found using integration. And that's kind of expected because 360 payments per year is quite a lot of payments. So it should almost be like the payments are being made continuously.